I'm going to talk about our recent development of adjustable coupling and in situ variable frequency EPR probe with loop gap resonators that can be used to carry out EPR spectroscopy from a sub-gigahertz frequency range up to X-band frequency range. So why we need in situ tuning, that's the first question. So usually in EPR spectroscopy, the frequency is kept constant and the magnetic field is swept to occur the EPR spectra. But there are certain systems, certain spin systems where the magnetic field need to be constant and the frequency need to be tuned to adjust the frequency at the avoided level crossing, for example, to look EPR spectroscopy in an avoided level crossing, and other spin qubit system, especially this tunnel splitting. Once we tune at the minimum gap, we can look at the clock transition behavior of the molecular nanomagnets and other spin qubits, which is a technique to enhance the spin-spin coherence time in these systems. So currently we are looking different system. One of them is nickel-4 molecule, which is a spin-4 system at low temperature. This is the spin Hamiltonian is described in terms of longitudinal parameters, and also the tunnel splitting parameters are described by this S prime. The energy level diagram of this molecule when the magnetic field is applied along the easy axis of the molecule is given by this energy level diagram. Here you can see that there are the two slightly different energy levels for each state. This is because of the slightly different conformational state of the ligand molecule of nickel-4. The other system here we are studying currently, I mean, we just started, is vanadium-based metal organic framework, which is described by this Hamiltonian, and the easy spin simulation shows that at the low magnetic field and the low frequency range, there might be possible clock transition or at frequency below gigahertz range. So we are looking for the possible clock transition in this molecule. So as I discussed earlier, the different system to study the avoided level crossing, we need a different frequency range. For example, in the nickel-4, I'm going to talk about M is equal to 2 transition, who's at the zero field, the avoided level tunnel gap is about 4 gigahertz range. And in case of VOTPP, it is less than 1 gigahertz. So we need such a EPR probe system to study these kind of transition in these materials. So we came up with a loop gap resonator here, and to address that issue of EPR probe. And here is the loop gap resonator, which is as by the name, has a loop and a gap. The loop describes the inductance, and the gap describes the capacitance of the tank circuit, which is just like, behave like a tank circuit. All RF magnetic field is concentrated in the loops, and hence the sample is placed in the loop, and the electric field is concentrated into the gap. So in order to make it a tunable frequency, the one parameter that can be changed easily here is the epsilon. This is the permittivity of this gap. So we came with an idea like using a dielectric substrate or dielectric piece that can be moved in and out in this gap to change the resonant frequency of this resonator. So we made a complete design for our sample space, which is a quantum designs physical property measurement system, a sample chamber which for 9 Tesla magnetic field. The resonator is placed inside here in the seal. If we look the exploded view of this seal, here is the resonator, and the microwave is coupled to the resonator through this antenna, which is here L-shaped, which is just an inner conductor of a coax cable. And the dielectric here is just above this gap, and which can be moved up and down with the help of this external controller here to change the frequency of the resonator. So for that, we use our measurement is at low temperature, so we need a vacuum system to do this experiment under low pressure and at low temperature. So we need a vacuum seal assembly with the help of O-ring and all these parts that we fabricated in the machine shop. So here are the two external controller. One is to control the frequency of the resonator, and the other controls the coupling of the microwave to the resonator. Once we assemble this part and this design and the parts, this is our final probe, where the resonator is inside the seal, and it is controlled with these external knobs that are present outside of the sample chamber. So, in order to characterize the resonator, we took a 4.5 gigahertz loop gap resonator and used a sapphire dielectric to tune the frequency all the way from 3.5 gigahertz up to 4.5 gigahertz. These resonance peaks are measured at the low temperature at 1.8 Kelvin. Just by changing the position of the dielectric. These are just a few spectra. We can adjust at any frequency within this the highest and lowest level, and you can see that the dip of each spectra is almost 30 dB, which is because of we can control this coupling of the antenna to the resonator, almost like a critical coupling, which we observe with vector network analyzer. So just measuring EPR, just measuring those reflection peaks are not sufficient. So for that, we use a nickel 4 molecule to actually use as a in EPR spectroscopy. This is a well-studied molecule, and the tunnel splitting gap of this M is equal to 2 state is previously measured in our group by multi-frequency measurement. These 3 different spectra are measured for different frequency, especially by changing the frequency by taking out the resonator from the sample space, which we can do now with the same. At one time, we can obtain multiple spectra just by putting the sample into in the loop of the resonator, and this resonance spectra is observed by in the VNA as a reflection. Here, this is observed as a change in the Q value of the resonator. You can see that at certain frequency, we see the 2 dips corresponding to the positive and the negative field. And we can change the frequency of the resonator easily just by tuning that. And we have another spectra that has a different resonant position here. So we can obtain as much spectra as possible with this resonator. While going a certain high frequency, we can see that the doubling of the spectra, which is because of the transition from both the energy levels from both the conformational state. So in order to extend our spectrum range more than that, we used a different resonator. Here we have this, we use this B and C, like this is for the, from the resonator B, and we obtained other spectra, this orange spectra from the resonator C. And we also calculated this resonant position for each peak by using a Lorentzian fit of this data set. And finally, we fitted these resonant positions with this formula, which gives the tunnel splitting parameters, which you can see that we have obtained a better precision in this time than the last time. So currently, we just started this molecule metal organic framework. For that, we need to go lower frequency, and we change our design here, and the sample is at the center here. And we have obtained some initial spectra here with the CW, which shows that there are some transitions, but we are not yet sure whether this is from the avoided label or just like hyperfine splitting labels. So that I would like to conclude my talks with the just simple design. We can change the multiple frequency, and also we can cover a wide range of frequency with the loop gap resonator design. And with that, I would like to thank our group and also the funding agency. Sorry for all the time.
Thank you, Gajadhar. Are there any questions for the speaker? Okay, I don't see any.